So good morning, everyone. Now let's see a few solved examples on DC choppers. Here is an example taken from Power Electronics by MD Singh textbook. Let's see the problem. A DC shunt motor takes a current of 80 amperes on a 480 volts supply and runs at 960 RPM. So the shunt, it is a shunt motor and taking 80 amperes of current from the supply, and the voltage is 480 volts with the speed of 960 RPM. The armature resistance is 0.25 ohms and the field resistance is 120 ohm. A chopper is used to control the speed of the motor in the range of 400 to 750 RPM. So a chopper circuit is taken to control the speed range from 400 to 750. So in between this range, the chopper circuit is going to control the speed. Having constant torque. So the torque is constant here. The on time period of the chopper is 3 milliseconds. So the T on time period is 3 milliseconds. T on is 3 milliseconds. 3 milli means 3 into 10 power minus 3. The field is supplied directly from the 480 volt supply. So the armature circuit and the field circuit both are supplied from a 480 voltage supply. Determine the range of frequencies of the chopper. So we need to determine the operating range of the frequency of the chopper. How we can calculate the frequency? Okay, let's see first the circuit diagram. See here it is a DC shunt motor. So shunt motor means if you shunt motor and separately excited motor, both are almost same. So don't bother that we haven't seen shunt motor in our syllabus. Don't bother about that. So generally the shunt and the armature windings both are connected in parallel. Okay, suppose this is armature. So the current in that will be armature current, and this is the shunt or separately excited machine, which the field is connected in parallel. Okay, so here it is connected to a chopper circuit. So this is any chopper circuit. Okay, any of the chopper circuit, and this chopper circuit is fed by a DC supply. So this is the DC supply. The voltage of this DC supply is 480 volts. So this is 480 volts DC supply. And from this DC supply, the current drawn by the motor is 80 amperes. So 80 amperes current is taking by the motor, which means the current is going means I'm sorry. Current is taking by the motor is 80 amperes. So that means these are the motor terminals. So these are the motor terminals. So the current that is entering at the motor is 80 amperes here. So 80 amperes current. Out of that, here he has given the supply is 480 volts and the armature resistance is 0.25 ohm. Field resistance is 120 ohm at 960 RPM. So these are the values at 960 RPM. So the speed is at 960 RPM, but we need to calculate the frequencies for 400 to 750 range. 400 to 750 range RPM. We need to calculate the frequency. But how we will calculate the frequency of the chopper? Frequency F is equal to 1 by T. Right? So frequency of the chopper means this T also belongs to total time period of the chopper. we have seen the T is on time plus off time. We know the time period is on time plus off time. So in order to determine the frequencies, we need to calculate this total time period. If we calculate the total time period, then we can calculate the frequencies for this particular range. Remember, the range, speed range is 400 to 750 RPM. So first we need to determine the back EMF for this 960 RPM. Because we have different speeds. So for different speeds, we will have a different back EMF, because the back EMF EB equal to K phi omega. So from this equation, EB, if K and phi are constant for a given motor, then EB is directly proportional to omega. A back EMF is directly proportional to omega. We need this relation because the speed is changing. That means the back EMF is changing. So initially, we will calculate this back EMF for the given 960 RPM speed. Okay, so in order to calculate the back EMF for 960 RPM speed, the back EMF formula of a DC shunt motor will be EB is equal to the input voltage EDC. EDC is the input voltage. Let us take EDC is input voltage minus IARA. So this is the back EMF formula, right? So RA is the armature resistance that is already given, which is 0.25 ohm. EDC is the supply voltage, which is 480 volts, that is also given. But what about this IA? IA is the armature current. But in the problem, he has given the total current, which is 80 amperes. Means the current taken by the motor is 80 amperes. So this current is dividing into armature circuit as well as the field circuit. So in order to calculate the current IA, we must calculate IF, because we know the field resistance, which is 480 ohm, sorry, 120 ohm. The field resistance is 120 ohm and the supply voltage is 480 volts. So the current through the IF will be, so here it is calculated, the field current through the motor, which is IF, will be VF by RF, means 480 by 120. So the field current is 4 amperes. So that means out of 80 amperes, 4 amperes is flowing in the field current. So what about this IA? IA will be 80 minus 4. The total current is 80 and 4 amperes is going into the field circuit. So that means 80 minus 4 will give 76 amperes. So now we have calculated the armature current. We know the armature resistance and we know the input voltage. Then we can calculate the back EMF at 960 RPM, because back EMF is related with the speed. So for different speed ranges, we need to determine a different back EMFs also. So in order to get that, we need to calculate the back EMF at 960 RPM. So using this formula, substitute EDC is 480 and IA is 76 amperes and resistance, armature resistance, that is 0.25. Then the back EMF is 461 volts. This back EMF is at 960 RPM. Okay. Now we have calculated the back EMF. Let's say that is EB1, back EMF 1 at 960 RPM. Let's say that is omega or N1. That is RPM, right? So we can say that is N1, let's say. Sorry, I'll erase this. So this is 960 RPM, which is speed 1, and the back EMF will be 461. So from the EB relation, we can write that EB 1 by EB2 equal to omega 1 by omega 2. Because EB is directly proportional to omega, that means EB1 by EB2 can be omega 1 by omega 2. So we need to calculate the speed range from 400 to 750 RPM. So I will consider the speed 2 as 400 RPM and speed 3 as 750 RPM. Between 2 and 3 only, the machine is going to control. So I know EB1, which is calculated as 461 volts. I know omega 1, which is 960 RPM, because EB1 is calculated at 960 RPM. So I know EB1, I know omega 1, and I know omega 2 or N2. You can say this is omega 1 or N1 because it is a ratio. So in the ratio, the 2 pi by 60 constants can be terminated. So omega 1 or N1, no problem. So here the omega 2 or N2 will be 400. So we know omega 2, we know omega 1, we know EB1, we can calculate EB2, which is the back EMF at 400 RPM. So using this relation, the back EMF at 400 RPM, which is EB2. So EB2 is 400 by 960 into 461 volts, which can be 191.88 volts is the back EMF at 400 RPM. So that means this is this back EMF will be EB2. So at 400 RPM, the back EMF is 191.88 volts. 191.88 volts. Okay, and similarly, at this particular instant, that means at 400 RPM, what will be the motor terminal voltage? That is the average voltage of the motor, EA, which is equal to EB2. Why EB2? EB2 is the back EMF at 400 RPM. Now we are calculating at 400 RPM, the motor terminal at the 400 RPM. So EA is equal to EB2 plus IARA. We know we have already calculated IA and we have calculated RA, which are constant for the particular DC operation, because here the torque is constant, so the current will be constant. So here the RA is 0.25 and IA is 76, but EB at 400 RPM is 191.88 volts. If you simplify this, you will get 210.88 volts is the average voltage of the motor at 400 RPM. Why we have calculated this EA? Because this is a chopper circuit, right? So I told you we have derived the average equation for the chopper circuit as EA equal to duty cycle D delta or alpha, you can say, into EDC. We know this formula. EDC is the input voltage. EA is the average voltage or the voltage across the motor terminal. D is the duty cycle. But we don't know the duty cycle. We know that duty cycle can also be written as a turn on time period by total time period T. So input voltage is EDC and the terminal voltage EA. We know EDC, we know turn on time. Now we have calculated EA at 400 RPM. So from this relation, we can calculate the total time period at 400 RPM. That is the starting starting speed range. So if we calculate the time period, then we can calculate the frequency. So this is why we have calculated EA here, terminal voltage, which is 210 volts. Now substitute EA and T1, which is given as 3 milliseconds. So that means 3 into 10 power minus 3. And EDC is 480 volts. So substitute all three values here and simplify for T. You will get T value as this. And frequency is 1 by T. That means you can get the frequency as 146.44 hertz at 400 RPM. Okay, so we have used this relation to calculate the time period. From the time period, we have calculated the frequency at 400 RPM. The same way we can calculate for 750 RPM also. The same way we can calculate for 750 RPM also. Let's see how we will do it. So for 750 RPM, first we need to calculate the back EMF. We know the relation between EB and speed, and we have seen that the previously. So EB1 by EB3 now. EB1 by EB3, because EB3 is the back EMF at 750 RPM. And N1 by or omega 1, you can write anything. Here the speed is given in RPM, so I am choosing N1 and N3. So N3 is the speed. We know EB1, which is 461 volts. We know N1, that is 960 RPM. And now N3 is the final speed range, which is 750 RPM. We need to calculate the back EMF at 750 RPM. So N3 will be 750 RPM. Now it is easy to calculate EB3 from this relation, right? So from this relation, the EB3 can be calculated, which means at 750 RPM, the EB3 is this one, 360.16 volts. Now we got the EB or EB3. Now we can get the terminal voltage as average voltage, a terminal voltage or average voltage of the armature voltage of the motor, that is EB plus IA into RA. We know IA, we know RA. Now we just calculated EB3. You'll get the terminal voltage at 750 RPM. Right. So at 750 RPM, we have calculated the terminal voltage. Now we know that EA is equal to D into EDC, where D can also be written as T by T on, sorry, T on by T, sorry, T on by T, T on by T into EDC, right? So this time period is related to 750 RPM, and this terminal voltage or the average voltage we have calculated at 750 RPM as 379.16 volts. So substitute this here. T on we know, which is 3 milliseconds, 3 into 10 power minus 3. Substitute T on value here, and EDC has 480 volts, I think. So substitute the 480 volts here. Now calculate the time taken for 750 RPM. So from that time, this is the time, and from this time we can calculate the frequency, which is 1 by T. So frequency is 1 by time period at 750 RPM, which is 263.31 hertz. So for 400 RPM, we got 146.44 hertz at 400 RPM. And at 750 RPM, it is 263.31. So he asked to calculate the frequency ranges from 400 RPM to 750 RPM. So the frequency range is from 146.44 hertz to 263.31 hertz is the chopper operating frequency for the given speed range. Okay, so this is how we can calculate the frequency range. Once again, I'll repeat once again. See here, a shunt motor is given, which means the field is separate and armature is separate. Shunt means the current is dividing and the total current is 80 amperes with a voltage supply of 480 volts. The motor base speed or rated speed as is 960 rpm. Armature resistance is given, field resistance is given, and the speed range is given. A chopper circuit is controlling this speed range. So we need to obtain the chopper frequencies to regulate this speed range. Okay, so for that we have we also have the on time period as 3 milliseconds. So in order to calculate the frequency, we need to calculate the time period. In order to get the time period, we need to use this relation, which is EA or the motor terminal voltage, EA or the average voltage is equal to duty cycle, which is T on by T, which is T on by T into DC supply voltage. Okay, we know the DC supply voltage, we know the turn on time. So we can calculate T so that we can achieve the frequency. So for that, we need to obtain this motor terminal voltage. So in order to obtain the motor terminal voltage, we need to calculate the back EMFs at particular speeds. So the same principle is used to calculate the back EMF. Initially, the back EMF is calculated for the base speed, which is 960 RPM. So for that, the armature current is calculated from the total current. Using the field parameters, the field current is calculated as 4 amperes. 80 minus 4 amperes will give the armature current. We know the armature current, armature resistance, and the total supply voltage. So the back EMF, which is EB1, can be calculated as 461 volts. Now, EB2 can be derived for 400 RPM with the relation EB1 by EB2 is equal to N1 by N2 or omega1 by omega2. From that relation, we can determine EB2, which is the back EMF at 400 RPM. So, which is 191.88 volts. From this, the voltage can be, the terminal voltage can be calculated, which is EA can be calculated for the first case. So, EA can be calculated. So, EA know at 400 RPM, turn on we know, and EDC we know, and we can calculate the time period. From the time period, we can estimate it, we can calculate the frequency. Similarly, the same thing can be done for 750 RPM also. So for 750 RPM also, we have done the same thing. So first, the back EMF at 750 RPM has been determined. And later, the terminal voltage is calculated, which is EA is equal to EB plus IARA. Using that formula, the terminal voltage at 750 RPM has been determined, or the average voltage has been determined. From this, with the formula, we can determine the time period. From the time period, the chopping frequency or the chopper frequency can be estimated. So the minimum range is 146 at 400 RPM and the maximum range is 263 at 750 RPM. So the total frequency range of the chopper will be 146.44 to 263.31 hertz. Okay. So this is how we can determine the chopping frequencies. Now, let's see another example. See here, this example is a DC motor example. A DC motor is fed from 600 volts DC source through a chopper. The DC motor has the following parameters. This is DC series motor. The series motor means armature winding and field winding both are connected in series. So the armature resistance is given 0.04 ohms. Field resistance has been given 0.06 ohms. And the constant K is given, which is 4 into 10 power minus 3 Newton meter per ampere square. This is DC series motor. Remember this. The average armature current is 300 amperes, which is a ripple free. So the armature current is 300 amperes. And the chopper duty cycle is 60%. Duty cycle D is 60%. Now, what we need to calculate? Input power, motor speed, and motor torque. So we have to calculate the input power, and we have to calculate the motor speed and motor torque. Let's see how to calculate the power. We know power, this is a DC. So the power can be the product of voltage and current. But we don't know the terminal voltage. So in order to achieve this terminal voltage, we know the relation between terminal voltage or the average voltage as alpha into VDC. So substitute alpha into VDC here. Okay. Alpha into VDC here. Now, if you substitute them, we know alpha is a duty cycle. See, some of the textbooks duty cycle may be determined as alpha. See here, you have seen this alpha as duty cycle. Now you can substitute 60% or 0.6 as alpha, and the supply voltage or the DC voltage is 600 volts. You can see that. Okay, so 600 volts. And next, IA, which is the armature current, directly given 300. Substitute here and calculate, you will get the power as 108 kilowatts. Very simple, voltage into current, substitute the values and calculate the power. And second bit, the motor speed of the motor. So speed of the motor means we need to determine, we need to calculate omega. So omega can be calculated with the help of a back EMF. We know the relation, we know this equation that EA is equal to EB. EB is the back EMF, EB plus IAR. See here, I'm pronouncing R because this is a series motor. In series motor, R, resistance R is RA plus field resistance RF. Both are connected in series, right? So RA plus RF are the gives the total resistance. So IAR. So EB can be written as K phi omega, or this is a series motor. So K into phi can be written as armature current because phi flux is a armature current in the DC series motor, and omega here. So K IA omega will be the back EMF, and IA into R. R can be RA plus RF. We know RA plus RF, we can substitute here. We know IA, which is 300 amperes, you can substitute here. K into IA into omega, we know K is given as 4 into 10 power minus 3 Newton meter per ampere square, substitute here. IA 300 amperes, substitute here. We need to determine this omega only. So we don't know the omega, but we need to calculate this terminal voltage. How this terminal voltage can be calculated? We know the formula, which is duty cycle, alpha or delta or D. You can use anything, alpha into input voltage, which is VDC or EDC. So the final equation will be like this. Okay, we know alpha as a 60%, which is 0.6, and DC voltage or the supply voltage as 600 volts. And substitute all other parameters here. Only the unknown parameter is omega, which we need to calculate. The second bit as motor speed. So simplify by substituting all these values and simplify this equation, you will get omega as 275 radians per second, or the speed means N in RPM as 2626.1 RPM. Okay. And next, third bit, we need to calculate the torque. We know the torque formula for DC series motor, which is some constant K into IA square. We know K directly given, IA is also directly given. Substitute them and simplify, we'll get the torque as 360 Newton meter. Okay, this is how we can calculate the input power, motor speed, as well as the motor torque for the given particular parameters. Here, see, it is a DC series motor, so the total resistance will be added. The total resistances will be added. Okay, remember this. Don't forget which type of motor that he has given. Okay, right. So with this, we can conclude the unit number 2. From the next class, we will start unit number 3. And other few problems will also be posted as a video in the YouTube. I'll tell you that. Okay. Thank you.